the sample's dropped into the cup, the oven, the quartz cup moves over, and then it raises into the oven, a very small oven, where we take the sample up to the maximum temperature that I'll show you. And what we do then is we start heating up the oven. We get a flow of helium going over the sample. We heat up the oven, and then with the mass spectrometer, which is right in this area, we sniff a little bit of that gas, and we measure the chemical constituents that come off. And as we do that, we capture a little bit of gas in our tunable laser spectrometer that was developed by Chris Webster's team out at JPL. And we capture a little bit more of the gas in a hydrocarbon trap, because one of our objectives of this experiment really is to search for organic compounds on Mars. And we later will send this gas to the gas chromatograph. I think I have a button here that'll make one of the columns light up. And then the gas goes through those columns, and the individual constituents come out one by one, and then back into the mass spectrometer through a back door. And again, we analyze what Mars is made of. And so if you go to the first graphic, we'll show you some of the data. And this really is just picking out the 5 major gases that were evolved from the sample. And let's start with what's labeled water on top, but the mass that we're monitoring that is mass 18. That's the signature of water. And you see the temperature scale on the bottom going all the way up to 1,500 degrees Fahrenheit in this case. And that water is coming off at really high temperature. And that's exactly characteristic of these smectite clays, and it's very good confirmation of what the ChemIn saw. We really do have clays here, and about 30% of the water that's coming off is at high temperature water. Go down to the lower left, you'll see a blue trace. That's oxygen. We've blown it up by about a factor of 10 in this case for illustration. And we did see some oxygen at our Rocknest dust pile, and we attributed that to the decomposition of a perchlorate, which is pretty interesting. It looks like there's very likely some perchlorate here as well. The red peak is likewise carbon dioxide. The carbon dioxide is produced either from oxygen reacting with carbon in the sample and making this carbon dioxide, or really the other alternative is a decomposition of a carbonate. And both of those possibilities are just fascinating, so that's what we'll be pursuing as we progress with new samples and so on. And then finally in the bottom right, at higher temperatures, you see masses labeled 64 and 34. And those represent an oxidized and a reduced form of sulfur. They represent respectively sulfur dioxide and hydrogen sulfide. And so that's just fascinating. We have both oxidized and much more than in this atmospheric dust, much more reduced sulfur there as well. What the tunable laser spectrometer was doing in the meantime in this experiment was measuring the deuterium to hydrogen ratio in water. And a very interesting observation, we had measured a very high deuterium to hydrogen ratio in water evolved from the dust. And we understand that as being a signature of a good fraction of water having been lost from the Mars atmosphere over geological time. And in this sample, we see just the lowest deuterium to hydrogen ratio that we've seen in evolved gas so far. And so that's something we're definitely going to be pursuing as we go forward with other samples. So go to the next slide. And here's what the search for organics is looking like. The data looks like signatures of mass to charge, just as I showed in the previous time. But here these compounds are coming out of the end of the gas chromatograph column. And here we see 2 compounds that we actually had also detected at Rocknest. Very simple chloromethane and dichloromethane compounds. And it looks like they're above the background level. It looks like they're there. We have to be very careful at this point in interpretation. This was the very first sample that had gone through the Curiosity drill. And so there's always a possibility that some residual carbon that was on the drill bit made its way into this sample. So we're really looking forward to repeating this experiment and seeing if these signatures of simple chloromethane compounds persist. So the really good news is the instrument is just working beautifully. It's a credit to the very talented team that worked hard on not only making this stuff, but making it robust and making it work in this very difficult environment on Mars. So with that, I'll turn it back to John for some additional comments.
Great, thanks, Paul. So what I'd like to do now is sort of set the stage a little bit for what we view in this mission as the transition from the original goal a decade ago of the search for water on Mars to now the search for habitable environments on Mars. And if we go to the first display item there, what we can see are two rocks separated by a decade of research. The one on the left is from the Opportunity rover back in 2004, a rock called Watmay. And what you see here is a rock. These images have been processed by Mike Malin and Jim Bell with what's called white balance, and it helps bring out our terrestrial intuition to sort of get a sense of what these rocks would look like if they were on Earth. The one on the left is basically from the sequence of rocks at Meridiani Planum, a rock that is reasonably fine-grained. The particles were either formed in water or transported in water. It was then cemented in water, converted from sediment into rock. And then after that, it was fractured, and then some of the fractures were filled in with what looks like a relatively thin material in this particular rock. But you see all the bumps sticking out. Those are the famous blueberries. These things we know are concretions. Well, it turns out these things are turning up on Mars, and here on the right is our rock in the Yellowknife Bay area called Sheepbed Unit, we've named it. And again, you can see it approximately has the same color on the surface. It's laced with these features that look like concretions to us. And the big difference is that you can see in that rock that it has a white vein fill running through it. That's the thing that ChemCam first hit and told us that there were probably sulfates here. So texturally, you see rocks that were transported in water, formed in water, cemented in water, altered in water, and but that's what you get on the surface. And so what we need to do is scratch below the surface, and if you go to the next one, this is what a decade of engineering gives you. On the left, there's a rock that was one of the first rocks that we ever interacted with at Meridiani with the rock abrasion tool. And on the right, we have the drill hole from Curiosity. And the drill hole is about 1/3 of the size of the rat hole there on the left. But the big story is in the powder that's generated. And so as we learned at Meridiani, we have a rock that is composed significantly of hematite in addition to these sulfates, iron-bearing sulfates that indicate very acidic waters. On the right, we get to see the new Mars, the gray Mars, that one that suggests habitability that has these clays and other minerals present. So what then do we mean by habitability? The key thing here is an environment that a microbe could have lived in and maybe even prospered in. So there's three things that we want to point out today that Dave and Paul have shown you. And the first issue comes down to acidity. We don't see any of the evidence that we have here, the rock on the left, the one from Meridiani. It's totally different in the subsurface in this rock on the right. We have the clay minerals, which form a neutral pH. We don't see the iron sulfates, which indicate acid pH. Instead, we see calcium sulfate. This rock, quite frankly, looks like a typical thing that we would get on Earth. And it's a neutral pH environment. And I think everybody has a sense of what acidity means, but there are some microbes that exist at very, very low pHs. But wait, there's more. And the second point is water activity. This is how much available water there was for a microorganism to live in its environment. So with that, I'm going to pull out a prop here. It's a jar of honey. Everybody always wonders why it is the solution of water and sugar can last on the shelf forever and ever without spoiling. And the reason why is that even though there's a lot of water in this honey, there's not enough that's available for a microorganism. And if a microorganism winds up in here, all the water will be sucked out of the cell. It's this thing called osmosis. The organism won't be able to live. Turns out the rock on the left there, that's what we think happened at Meridiani, but instead of sugar, we had a salt called magnesium sulfate. And there was so much of it that it would have inhibited microorganisms to live there. That was not a habitable environment. And then there's one more thing that we're really excited about that we found at Meridiani, at Gale, and it's a battery. And basically, these minerals that Dave and Paul were telling you about, they're effectively like batteries. Some of them are negatively charged, and they have various oxidation states. And what we have learned in the last 20 years of modern microbiology is that very primitive organisms they can derive energy just by feeding on rocks. So when Paul talks about sulfate versus sulfide, and Dave talks about clays and magnetite, these are the kind of things that tell you that there could have been a flow of electrons in the environment. Just like on this battery, you hook up the wires and it goes to the light bulb and the light bulb turns on. That's kind of what a microorganism would have done in this environment if life had ever evolved on Mars and if it was present here. So that's what we mean by habitability. Take all three of those factors, and to really understand that, that's what we built this payload for, and that's what we feel that we've succeeded at. And so with that, I'll turn it back to Dwayne.
Thank you, gentlemen. Okay, we're going to open it up for questions. Now, normally I would start here in Washington, but we're going to go out to the West Coast first and then come back to the Jet Propulsion Laboratory.
Hi, how's it going? NBC in Los Angeles. So can you talk to me a little bit about the area where the rock was found? What would it have been like in ancient times? What would we have seen there?
Okay, so what we imagine it would have looked like was the picture that Dave showed. We feel is a pretty good representation. It's conservative in the sense that it shows a lake bed that's dry. The lake bed was filled by sediment derived from streams, but we don't know how long-lived it was. And so that's always a challenge we've got on Mars. It's not like the rocks come with numbers on them to tell you how long the water was there or how much there was there ultimately. But we believe that we wound up in this sheepbed unit at a place that was wet for a relatively long period of time, enough for all these chemical reactions to occur.
Okay, now we're gonna come back to NASA headquarters. Any questions from our media here in the front row? Okay, so what I will do then is let's go to our social media community for a couple of questions that have come in to me. And then we're going to go to Alan Boyle, but let me take the social media question first. Clearly, NASA knows how to build rovers. What will the 2020 rover look like, or be able to do the same capabilities?
One of the things that we're planning with the 2020 rover, we now have a great capability in the entry, descent, and landing system and the rover system that we built for Curiosity. We want to use as much of that as possible in the 2020 rover, and so the approach that we're taking is to use that descent, landing capability and the rover as a platform for the 2020 mission, but we're going to populate it with new instruments and new capabilities, maybe in the arm, and for instance, maybe doing coring instead of drilling. So that's sort of in the mix, but we're going to start with the basic rover and a system to get it to the surface safely. And because of that, I think we will be able to, let's say, not have to do a lot of the engineering development that was required for Curiosity, save a fair amount of money, and get also a very capable rover system to the surface of Mars with the newest and best instruments that we have available at the time.
Okay, now let's go to the phone lines, and I believe we have Alan Boyle up first in the queue. Alan?
Hi, thank you. Alan Boyle from NBC News. I just had a general question about how do you feel that it sounds like you're all excited about this, and do you feel like it's mission accomplished? What went into nailing down these sorts of results? Can you describe a little bit of the emotion behind the process? Thank you.
Well, I'll start with sort of the whole idea of where to land on Mars with this tremendous asset. When it came down to it, we narrowed our landing sites down to 4, and all of them looked really good. And as you might imagine, every single scientist had their favorite. And so we had 4 major contenders. And I kept on thinking, now that we picked Gale Crater to go to, that the odds are 75% that we picked the wrong place to go. Well, you can imagine relief. landing there, and then almost right off the bat, we do find evidence of water. We see a ancient riverbed. We're now finding an environment in the near subsurface, not too far beneath the oxidized layer, of finding sort of a